Okay, so we are finally moving on a little bit past limits into another major calculus topic, which is about continuity. So this is section 4.5, part 1, talking about continuous functions, but different types of continuity than just the general idea. So I know that you guys have some general sense of continuity because we've talked about it all year in PreCalc, that if you can trace along a graph and never have to pick up your pencil, then you're continuous everywhere. And then you kind of know some different types of discontinuity, right? If I were tracing along but I had a vertical asymptote and I have to move across my vertical asymptote, then I have infinite discontinuity because around that vertical asymptote, the arrows would be going towards some kind of infinity. Maybe the same, maybe different, but we would be going towards some kind of infinity. Or if I literally have to jump from one branch to a totally different branch, I have a jump discontinuity. Or if I just have a point disco, right? That's what point disco stands for. I have a point discontinuity. I just have to go over top of my little point that's an open dot, and then I continue down the same path. So we know you have some general sense of that, but the first thing that we're going to have you do in section 4.5 is actually a really specific definition, and this 3-part definition for being continuous at a certain point. So not about looking at a graph as a whole, but looking about one certain C value. So the C variable that they're using is the point that you're talking about your 3-part definition on. So this is something, you guys, that you will not just see in PreCalc. You will definitely see it in calculus. We talk about it at the beginning of the year. We talk about it at the end of the year when we're reviewing for the AP exam. It's a really important definition that you have to know. And it's one of those things that you kind of have to go exactly the way we teach it in the certain order of all 3 parts with good notation, or you would never get the points on the AP exam. So part 1 is that your function must be defined as x equals c, which just means that f of c, when you plug in c as your input, you get out an output. You get a y value out. So f of c exists, or f of c is defined. In the algebra world, the only way this is not going to work, right, that you're not going to be defined, is if you try and plug into your function your c and you got division by 0. So in a rule, if you got division by 0, then your f of c would be undefined, and you would break condition number 1. So I always talk to my kids about, you have to meet all 3 parts. If you break a part earlier than step 3, then you say, therefore my function is discontinuous at whatever my c value is. So you don't have to keep going if you break condition number 1. But typically this part works and you move on to condition number 2. So condition number 2 is that the limit as x approaches c, which is why we do limits before we do continuity, the limit as x approaches c of f of x exists, which means you have a limit answer. So when you're doing your limit, you get an answer out. You might have to finagle to do that. And in order to get an answer out, doesn't that really mean that the one-sided limits match each other? And you don't always have to worry about the one-sided limits, but just to put that in your brain, to watch for that, that also means the limit as x approaches c from the left of our function has to equal the limit as x approaches c from the right of our function. So our left-hand limit has to equal our right-hand limit. LHL has to equal RHL. So the whole 2-sided limit exists, and we can meet definition 2. And as we go through examples, you'll see how sometimes this condition is broken. And then the third part is that the limit as x approaches c of f of x, that our limit answer that we got on step 2 equals f of c, our function value that we got on step 1. That they essentially match, that the 2 things that you did in part 1 and part 2 match. And if they match, because sometimes they would be different, then you've met condition 3. And if you've met all 3 conditions, then you would wrap it up and you would say, therefore, yes, our function f of x is continuous at x equals c. And you have to restate this because it might not be continuous everywhere, but the 3-part definition that you're proving is proving that it's continuous at that c value. Or if one of the conditions was broken, then you would say no. Therefore, f of x is discontinuous or not continuous at x equals c. Okay? So that's kind of what we're going into. So I'm going to try and keep this 3-part definition kind of up on the board so the notation's there as we keep going through the examples so we can kind of keep referring to it. But we're going to start with examples that all have the same directions. So decide if the following functions are continuous at c equals 2. So for letter A, we're given the function f of x equals negative absolute value of x minus 2, close your absolute value bars, behind that plus 4. So especially at the beginning, sometimes it's nice to go through these a little bit in a graphical way. So I'm going to teach a little bit of it just from a graphical standpoint and how you would go through the 3 parts, just analyzing the graph. And then we'll do some like in the more algebra way. And you'll see that you get the same answer either way. But at first, just to like have the concrete and have the visual and like get it wrapped in your brain, I think it helps to graph. So let's graph this. So not like anything kind of crazy, just like a pretty typical transformation, right? We have absolute value. Oh yeah, that's going to be a V. Oh, our V is going to open upside down, and we have to do any reflections and stretches or shrinks before we shift. So our V is going to open upside down, but it's also going to be shifted, what, right 2 and up 4? Okay, so if I have my parent function, but then I know, oh, I got to flip it upside down because of the reflection because the A is a -1. Oh, but then I got to shift it because I need to go right 2 since I'm inside the house and the H is a 2, and I need to go up 4. Oh, so then every dot I see, I shift right 2 and up 4 because it really is just absolute value, and the vertical stretch and shrink is not affected because there's still that understood 1. It's really like the slope of each line that are forming at that vertex to make the V. So aren't we going, in this case, down 1 over 1, down 1 over 1 to keep it symmetric, down 1 over 1, down 1 over 1, and here's our final graph. So maybe erasing this little intermediate step that I have. Okay? So we're like, all right, cool, there's a graph. So if I'm going through this 3-part definition, because we're talking about continuity at a certain point, and some of you might go, I already know absolute value is continuous. Like I can trace on this V and never have to pick up my pencil. Great, you still got to prove it by the 3 parts if we're talking about a certain point. So I would label the 3-part definition. I would say, here's me doing step 1. Here's me doing step 2. Here's me doing step 3. Unless a part's broken and you can bail on that problem and say it's not continuous or discontinuous. So step 1 is that f of c exists. Well, isn't our c 2? So f of 2, I'm analyzing it from the graph, means plug in 2 for your input. What output do you get? Oh, well at 2, we're lined up with the output of 4. So f of 2 equals 4. So f of 2 exists. Or you could say f of 2 is defined. If I plugged it into my rule, 2 minus 2 would be 0. The absolute value of 0 is 0. Negative 0 is still 0. And 0 plus 4 is 4. I get the same thing. So f of 2 exists. So part 1 is met, and we're moving on. Part 2, you got to have good notation. The limit as x approaches c. Our c is 2. So we write the limit as x approaches 2. Remember, you guys, you have to take the limit of something. So if I'm analyzing it graphically, isn't this my graph of f of x? So maybe instead of rewriting this whole great big rule, maybe I just want to write f of x here. You got to have the limit of something, but if we've defined it as a function for you, you can write that function notation. Well, if I have a graph, like this is back to like the very beginning of what we did with limits approaching a c graphically at the beginning of section 4.4, part 1. Oh yeah, the closer and closer and closer I get to 2 from the left. So if I make it L with my left hand, the closer and closer and closer I get to 2 from the left, would I be getting closer and closer and closer to the target of 4? The closer and closer I get to 2 from the right, wouldn't I be getting closer and closer and closer to the target of 4? Both sides are approaching the same value. Everything's good to go. I have the same target. So the limit as x approaches 2 of f of x equals 4. So my limit exists, which was what had to happen in part 2. We had to get a limit answer. And in this case, I didn't have to like show anything really. I'm just analyzing the graph from the left and right, and as long as they're approaching the same target from both sides, my two-sided limit exists, and this means my two-sided limit. I'd have to have the little negative or positive in the upper right-hand corner to be the one-sided limit, and I don't need to say that if they're approaching the same value. I can just analyze the two-sided limit. So part 3 is kind of a test. Is the limit as x approaching 2 of f of x, giving us and matching the exact same answer as we got when we plugged in 2 for c. When we just plugged it into our function, does it equal f of 2? Well, my limit answer was 4, and my f of 2 answer from part 1 was 4. This is a true statement, right? This is checking out. This is working for me for part 3. So on this problem, therefore, yes, right? F of x, because that was how our function was defined, is continuous at x equals 2. You have to restate the particular c value you were testing, because you might have something that's not continuous everywhere, but it's continuous at the certain point you just did your 3-part definition on. So part A, everything's cool, all 3 parts are met, and the notation looks good, and we're moving on to part B. So we're like, okay, cool, part B. So in part B, I'm not even going to give you the algebra rule. We're just going to go straight from a graph. So I said we're going to kind of mix it up, and then I'll show you somewhere you could do it either way. So on part B, again, keeping our three-part definition over there, we have this graph, mostly emphasizing quadrant 1, if you want to join in graph with me. We have an open dot at 2, 1. We have a dot at 3, 0 on top of our x-axis, and a little diagonal line going like that. We have a closed dot at 2, 2, and we have a open dot at 2, 4, with the arrow shooting off this way. And let's say that they've labeled this the graph of g of x. And we still have the same directions that we're trying to figure out and decide if the following functions are continuous at c equals 2. So we're still testing the three-part definition at the x value of 2 if our c value is 2. So if we're testing the three-part definition, then we want to go ahead and label all three parts, right? So part 1 is, does f, not f because it's g, does g of 2 exist? So can we plug in 2 as an input, and can we get out an output? And we don't have a rule actually on this one, we just have the graph, so we don't have a rule to like test it into to see if it gives us division by 0 in the denominator. That would be the only way in the rule that it would be undefined and not exist or not be defined. Well, do watch your letters, so depending on whether it's F or G or H or P or whatever letter they want to use, kind of watch that because you need to make sure your three-part definition follows the original function notation that you had. Well, G of 2, you guys, you got to be careful. Isn't G of 2 the output of 2? This is still a function. It passes the vertical line test because right here at 2, we only hit one dot. The dot we hit is a closed dot. We're not hitting the open dots. So G of 2 equals 2. So G of 2 exists, or G of 2 is defined. So part 1 is met. Part 2 is the limit. Does the limit as x approaches 2 of our function g of x give us a limit answer out? Well, unfortunately on this one, we're going to have to do the one-sided limits. If I think about the two-sided limit, in order for the two-sided limit to exist, the one-sided limits have to match. So if I thought about the limit as x approaches 2 from the left, so I do my little negative sign in the upper right-hand corner, of my function g of x, the closer and closer, I'm on my left hand with making it L on my left hand, the closer and closer and closer I get to 2 from the left, right? I'd be in between 1 and 2. Wouldn't I be up here at this path? Think about a little bug. He would be going and traveling down to this target, which is 4. But the limit as x approaches 2 from the right of g of x, you got to have the limit of something. You got to put your function notation there. Well, from the right-hand side, I'd be a little bit beyond 2. Think about being in between 2 and 3. I'd be getting closer and closer and closer and closer and closer to 2 from the right, from the right, from the right. Well, now my little bug's way down here on this path, and he's getting closer and closer and closer and closer to that open dot where the target is 1. It doesn't matter that it's an open dot. The limit target exists. You're getting closer and closer and closer to 1. Well, isn't that not good? Right? This left-hand limit answer of 4 does not equal this right-hand limit answer of 1. Therefore, the two-sided limit does not exist. So that DNE stands for does not exist. Or you think amigos, oh, the limit does not exist, right? And you wear pink. We're not wearing pink, but pretend. So if condition number 2 is broken, because I didn't get a limit answer out, the limit does not exist, I don't need to move on. I don't need to talk about condition 3, the limit didn't even exist. So I stop as soon as I realize condition number 2 is broken. So therefore, no, g of x is not continuous at x equals 2. Again, there might be other spots where it's fine, but that spot fails the three-part definition. So you have to restate your x value. Okay, so as soon as one of the parts fail, you kind of bail and you have to wrap it up. You can just say therefore and say this because all of this other work is proving that. Okay, so part C. Again, this one I'm just going to give you the graph for and not a rule for. And we'll kind of just analyze it graphically. But same directions on all of these. We're using this three-part definition and trying to decide whether or not we're continuous at C equaling 2. So part C, we have, again, mostly quadrant 1. We have a closed dot at 2, 2. We have an open dot at 2, 4. And we have a graph that looks something like this. Okay, and this graph is labeled the graph of n of x, let's say. So we're still focusing on our x value or our c value being 2, and if we are talking about continuity at a specific point, it's the 3-part definition. So we go through it very rotely every time. Part 1, part 2, part 3, the same organization every time. So part 1 is, does our function value exist? But our function is labeled as n. So does n of 2 exist? Is n of 2 defined? Which means, can you plug into and can you get an output? Well, if you don't have a rule to plug it into to see if you get an output, you're thinking, well, when I plug into it, do I get a spot on the graph? Yeah, when I plug into, I get a spot on the graph. It's this closed dot right here at 2. Because this spot's an open dot. This is a point disco. So this is not going to be where the function's defined to be. The function's defined to be at 2, 2. So n of 2 equals 2. So n of 2 is defined, or n of 2 exists. You can use either one of those words, but part 1 is met and we move on. The only way part 1 would not be met on a graph is if you had a vertical asymptote or an open dot without a closed dot to match up with the input value, or on a rule if you got something that had division by 0. Part 2 is all about the limit. So we write out our limit notation. Does a limit as x approaches 2 of our graph n of x give me an answer? Well, if I'm doing a limit as x approaches 2 and I just have a graph and I don't have a rule to try and evaluate the limit algebraically, then think back to what you did first in 4.4. Oh, the closer and closer and closer I get to 2 from the left, I'd be in between 1 and 2, coming in from the left-hand side. Oh, well, I'd be up here on my path. This is a single dot. That's not the path that I'm on. And I'd be getting closer and closer and closer and closer to what target? Oh, my little bug would be going towards a target of 4 from the left. So in order for this two-sided limit to exist, the one-sided limits have to be the same. Well, this one's going towards 4. Well, the limit as x is approaching 2 from the right. Well, that would mean I'd be a little bit beyond 2. Think about being in between 2 and 3. Coming in from the right, coming in from the right. To the right of 2. Oh, wouldn't my little bug be up here on this path? Because how does he jump down to this one closed dot? He's on this path, and he's approaching what target? Oh, he's approaching the same target of 4. So this one equals the limit as x approaches 2 from the right of n of x. And you could write them as 2 separate statements. I'm just showing you how you could string it together. They both equal the same target. That means that this limit answer, the two-sided limit, equals 4. So part 2 is fine. The limit exists. So my function value is defined for n at 2. Function exists. Check mark. My limit existed because my left-hand limit did equal my right-hand limit. They both equaled the same answer of 4, so my two-sided limit answer was 4. My limit had an answer. It exists. So now I'm on step 3. I have to keep going. I haven't failed any part of the 3-part definition yet. So step 3. Does the limit as x approaches c of my function equal what my f of c answer was from part 1? Well, my limit as x approaches 2, my function was n of x, equals n of 2, because, no, actually it does not equal n of 2, because this answer was 4, right, for my limit, but this answer was 2. They do not equal each other. This part's false. So that's how you could fail part 3, even though part 1 and part 2 were met. They don't match at the end. They have to match at the end in order for us to give a conclusion of, yes, you are continuous. So this conclusion would say, therefore, no, n of x is not continuous, or you could say discontinuous. Last time I said not continuous, so this time I'm going to say discontinuous, at x equals 2. Make sure and restate that x value. So out on that one. Okay? So the last one we're going to do all algebra-wise instead of showing any kind of graph. So you get used to both ways. Sometimes it might not be super doable to graph, and you might just have to be able to be comfortable with your 3-part definition, all from an algebra standpoint. So I would try this one algebraically on your own, see how you do, and then you can always pause the video and join back in, and then we'll do one last kind of hurrah. So our rule that we're going to be using, and I'm just going to do this notation just so you can see this notation too. Instead of function notation, I'm going to say y equals x cubed. So we still want to know whether or not we're continuous at the c value of 2. Okay? So if I pause the video right now for you guys. Pause the video right now. Try it on your own, and you go through all 3 parts. And if you pause the video, I'll try and move out of the way. There's your 3 parts that you can kind of look at when it's paused with good notation. And then try and rejoin in. So I'm assuming you've joined in. So part 1 of the 3-part definition is, does the function value exist? So if I plug in 2, do I get out an answer? Well, if I try to plug in 2 to my rule for y equals 2 cubed, oh yeah, y would equal 8. So part 1's fine because I can plug in 2. So y of 2 exists. Or you could say y of 2 is defined. I didn't get division by 0. So part 1, totally okay. Part 2 of the 3-part definition. Does the limit as x approaches 2 of my rule, you could put a y here instead of f of x or g of x or h of x. Does that limit have an answer? Does the limit exist? Well, you guys, if you're not looking at it graphically, because you don't always have to look at it graphically, then you, instead of maybe wanting to leave this as y, actually want to put the rule for y. So our rule for y was x cubed. Well, isn't the first thing that we try with limits? The first thing that we try with limits is direct substitution. I don't have anything even in a denominator to give me 0 over 0 or a number divided by 0 to make it a weird limit. Don't I just directly substitute? So I'm plugging in 2 in place of x. That's why the limit notation goes away, and 2 cubed is 8. Oh yeah, so this limit answer is 8. It worked with direct substitution, so my limit exists. So I'm moving on because part 1 was met. It worked cool. Part 2 was met. It worked out fine. It's cool. So now I'm on part 3. Does my limit as x approaches 2 of y, because that's how we denoted this instead of function notation this time, equal what I got when I plugged in y of 2? Well, my limit answer was 8 from part 2. My function value is 8 from part 1. This is a true statement. This works. So therefore, yes. Our y equals x cubed rule is continuous at x equals 2. All 3 parts were met. So remember that if you're trying it and you're not looking at it graphically, the first thing you try as a limit approaches a c is direct substitution. Most of the time for these problems, I'm thinking direct substitution is going to work and you won't even need to do any finagling if you get down to the limit stuff. Okay? So we're going to do one more, and this one I'll kind of show you both ways, maybe like graphing and the algebra way, so you can kind of get your head wrapped around either option. Okay, so this one is a biggie. So we have, first of all, a piecewise function. What? So draw your brace, big enough for 3 pieces. X squared if x is greater than negative 2. 1 if x is equal to negative 2. And 2x if x is less than negative 2. And we're going to change our directions to decide if the following function, let's say instead of r, is continuous at c equals negative 2 and at c equals 1. So we're going to test like 2 spots. So if it's a piecewise graph, you might want to look at it actually graphically first. So if I graph this, and then go through my 3-part definition to talk about continuity at a point. Kind of looks like we have this critical spot at negative 2, right? Like that's where our pieces are all changing. So this would just be our normal parent function for a parabola, but instead of maybe seeing all of it, we're going to see the piece that's defined with the domain x is greater than negative 2. So if I went to negative 2, even though it's just x is greater than negative 2, I'd still have to plug it in to know what output I would get close to. So negative 2 squared would give us 4. But wouldn't it be an open dot at that critical point? And then if I want to be greater than negative 2, wouldn't I want to go to where I'm bigger? So negative 1, if I plugged it in, negative 1 squared would give me negative 1 times negative 1 would be positive 1. If I plugged in 0, I'd get 0. Oh yeah, if I plugged in 1, oh yeah, these are my other like very important points. If I plugged in 2, I'd be at 4. This is just kind of helping me connect, so don't I have a lot of my parabola, but I just don't see like the rest of this going up and up and up forever. It looks like f of x is supposed to equal 1 if x equals negative 2. So a lot of times you guys on piecewise, if you have a constant, you're like, oh, that's going to be a portion of a constant horizontal line. But this is 1 if x just equals negative 2. Doesn't that mean that this is just a single dot? If you plug in negative 2 for x, you get out 1 for y, or for f of x. It's just like a single dot. So negative 2 maps to 1. And then f of x equals 2x is just going to be a diagonal line with the y-intercept of 0 and a slope of 2. But we don't really see that y-intercept because we only want the domain when x is less than negative 2. So like here's like your dotted line, if you drew a dotted line like Hernie does to split it up. And you would be on this side of it. Or if you think about how I do it with the table, you would plug in negative 2. Even though it doesn't say equal, you got to know where you're close to. So if I do 2 times negative 2, I'd be down at negative 4. It's just an open dot there because I don't equal that. And then I'm going to use a slope of up 2 over 1, but if I went up 2 over 1, I wouldn't pass the vertical line test. Oh, so how about we go down 2 and left 1 so that we know some other points along this line. Down 2 and left 1. Oh, so it's like this. Okay? So there's my graph. I'll show you kind of both ways. So if we start by discussing the continuity when c is equal to negative 2. So part 1 is, okay, does the function value exist? Well, this was an f rule, and f of negative 2, I could plug in to the piecewise rule. F of negative 2, right when x is negative 2, I'm supposed to get out 1. Oh, yeah, it's 1. Or if you're looking at the graph, isn't negative 2 lining up with a closed dot at 1? These are open dots, so that's not where the function's defined to be. So f of negative 2 exists. Part 1 is met just fine. Part 2 is the limit. So we want to know what's the limit as x approaches negative 2 of this function f of x. So I don't know if we've done yet like a limit algebraically on piecewise. So this is like a really good one to show you algebra-wise. So if we wanted to do the limit on piecewise, but the limit c value that we're looking at is where like the pieces are based off of, like the critical point, you're going to have to do the pieces separately. That's why we have this one-sided limit notation. So the limit as x approaches negative 2. Ooh, this is weird, because you got the negative 2 from the left. Don't you like that? The negative 2 and then the negative in the upper right corner meaning from the left. If you were approaching negative 2 from the left, right? Here's my L on my left hand. Wouldn't I be in between negative 3 and negative 2? So I'd be smaller than negative 2. So wouldn't that be this bottom piece of the piecewise? So if I were just doing it graphically, I could say of f of x, and I could look at it graphically and go, oh, that limit target is approaching the number of negative 4, if I were doing it graphically. If I were doing it algebraically, you would show the piece that that domain applies to. So negative 2 from the left would be the piece 2x. And 2x is not going to be anything that gives us division by 0 or 0 over 0 that we have to finagle. We can just directly substitute. It doesn't matter that it says negative 2 from the left. You would be plugging in negative 2 for this x. The other 2 would still be in front of it, which would give you negative 4. So same answer either way, which is like the point I'm trying to make. You can do it graphically or algebra-wise. Well, now if we try the limit as x approaches negative 2 from the right, so you do your little plus sign. If you were doing it graphically, you would write the limit as x approaches negative 2 with the plus sign to mean from the right of f of x. Well, if I were approaching negative 2 from the right, I'd be a little bit beyond negative 2. I'd be in between negative 2 and negative 1. Well, now my path would be the parabola path, right? I'd be going closer and closer and closer and closer and closer to the target of positive 4. This is just a single dot hanging down here where the function's defined. That's not the path you're on. So the target limit answer, as you're approaching negative 2 from the right, would end up being positive 4. Or, if you were doing it algebra-wise, the limit as x approaches negative 2 from the right, and you would use where x is a little bit bigger than negative 2. That would be from the right. That's the top piece of the piecewise function, the x squared piece. Well, it doesn't matter that it says from the right, negative 2 from the right, you still just plug in. Negative 2 squared, that's where your limit notation would go away because you've plugged something in. You would directly substitute, and negative 2 squared would give you positive 4, which was the same answer we got here. So actually, even though they're both 4s, if one's negative and one's positive, they are not the same thing. So the left-hand limit does not equal the right-hand limit, and this limit does not exist. So we just failed part 2. And if we failed part 2, we don't even go on to part 3, we would wrap this up and say, therefore, f of x is not continuous at x equals -2. You have to actually keep meeting each part to move on the 3-part definition. So if we real quick go over this same graph, so I'm not going to erase it, let's just do all the algebra way instead of a graphical way. And let's focus on the c value of 1. So part 1 would be, does f of 1 exist? Can I plug in 1 and can I get out an answer? Well, 1 would be greater than -2. So it would meet the top piece of the piecewise functions domain, and we'd only plug it in here, right? You can't plug it in to the pieces that it doesn't satisfy. It's not equal to -2, and it's not less than -2. It's only going to be plugged into here. And 1 squared will give us 1. So that means when I plug in 1, I get out 1, which does match on my graph. So yes, f of 1 exists. Part 2 would be the limit as x approaches 1 of our function f of x. Well, if you have something and it's piecewise, but where the pieces are breaking apart isn't the spot you're even talking about, why do you need to do from the left and do the right? Just plug it into the piece that satisfies. X equals 1 only satisfies this top piece where x is bigger than, greater than, -2. So you'd just be using the limit as x approaches 1 of that x squared piece. The first thing that we try with limits approaching a c is direct substitution. We can directly substitute this in. We don't even have a denominator, and 1 squared gives us 1. So our limit exists. And if we think about it graphically, the closer and closer and closer we get to 1 from either direction, the closer and closer we're going to the target of 1. Looks good, right? So part 3 is, does the limit as x approaches 1 of our function f of x equal what we got for f of 1 when we actually plugged that c value in? Well, our limit answer was 1, which we got on part 2. Our f of 1 answer in part 1 was 1. Oh, yep, 1 equals 1. This is true. Checks off. So couldn't we wrap it up and say, therefore, yes, f of x is continuous at x equals 1. Which, of course, if you graph it intuitively, you're going to know, because you're like, yep, I can trace right along here and never have to pick up my pencil. The only spot we have to pick up our pencil on is at -2. You guys probably already know graphically this is a jump discontinuity. You're just proving that jump discontinuity fails one of the parts of the 3-part definition when you prove that it's discontinuous at x equals -2. So it's like some of the stuff you already intuitively know, and now you're just proving it with the formal calculus way. Okay? Look for a problem like that. I think that's kind of what your homework looks a lot like. And also I would be looking for a problem like that maybe next week as like a little homework quiz, 1 question kind of thing with different numbers. Mr. Herney, any last minute thoughts?
Nope. Looks good.
Okay. See you guys later.